Welcome everyone in my YouTube channel. So let's come towards the video. In this video, we will discuss the final sem exam question paper of 8th sem semester of Master of Computer Application of International Institute of Professional Studies (DAVV). So let's come toward the question. The given question is give notation of representation of following component of formal languages. Here we have some options. The option number A is alphabet, B is string, the option C is empty string, option D is length of the string, and option A is prefixes and suffixes. Option F is languages and option G is operators on languages. Now let's come toward the answer. The option A for alphabet. Notation for alphabet is sigma. Option B is a string. Notation for string is W, S or A plus B asterisk. Option C is empty string. Notation for empty string is or option D is length of the string. Notation for length of the string is mod of W or mod of X. Option E, which is prefixes and suffixes. Notation for prefixes is TOC T2. Notation for suffixes is T2 TOC. The option F is which is languages. Notation for languages is L. Operators on languages, which is notation for operators on languages is intersection, union, concatenation, clean, star or complement. This is the second part of question 1. Define a finite automata of string by FA. So the answer is FA stands for finite automata. It is a mathematical model used in computer science for formal languages theory to represent a system that process input according to the set of rules. A finite automata consists of a finite set of state of transition between these states based on the input symbol and initially state or one or more state. Accepting of the string by the finite automata refers to the whether the finite automata give an input reaches to a accepting state or final state. After processing the entire input string, uh, the finite automata reaches an acceptability. It means that the input string is recognized by or accepted by the automata according to its defined rules. Otherwise, if the automata doesn't reach at the accepting state, then the reject string will be rejected. This is the third part of question 1. The question is give four difference between NFA and DFA. Certainly here are four important differences between NFA and DFA. The first one is an transition function. In DFA, for each state and input symbol there is exactly one transition leading to a next state. In NFA, for each state and input symbol there can be multiple possible transition leading to one or more next symbol. This non-deterministic allow for more flexible in the transition. The second one is acceptance criteria. A string is accepted by DFA if the DFA reaches as designated accepted instead after processing the entire input string. Or NFA, a string is accepted by NFA if there exists at least one path through the state of the NFA that lead to the accepting state after processing the entire input string. The third one is handling of rejecting input. In DFA, if there is no transition defined for a given state or input symbol, the machine gets stuck or rejected the input. And in the NFA, if there is no transition defined for given state and input symbol, the machine can simply ignore that input symbol and continue processing the input string. It only gets stuck if there are no valid transition at all. The fourth one is state space. In DFA, the state space is of DFA is typically larger compared to the NFA. Or in NFA, the state space of the NFA can be smaller than the DFA. This is the fourth part of question 1. In this question, we have some statement, then we have to identify that which statement is true or which is false. So the statement A is if L is a language accepted by NFA-M, then L is also accepted by DFA. The option statement B is for every NFA there exists an equivalent DFA that simulates the behavior of NFA. The statement C is in NFA to DFA conversion. For n slot NFA, there exists at most 2 n state in DFA. So the answer is the statement A is true. Statement B is also true. The statement C is. This is the question second. What are the regular set regular languages? What are valid operations used in regular expressions? So the answer is regular sets, also known as regular languages, are fundamental concept in formal languages theory and computer science. A regular language is a set of strings that can be described by the regular expression or recognized by a finite automata. These languages are simplest of most well-defined class of formal languages. In simple terms, regular language consists of patterns that can be represented using a finite set of rules. These rules typically involve simple operations like concatenation, alternation, and clean starts. And the class can be essential in areas such as matching and text processing and compiling design. The valid operations used in regular expression include: the first one is concatenation, combining two regular expressions to match string formatted by the concatenation of string matched by the original expression. The second one is a union alternation, combining two regular expressions to match string matched by either to the original expression. The third one is clean start, zero or more repetitions, matching the zero or more occurrence of the pattern described by the regular expression. The fourth one is a cleans plus, one or more repetition, similar to the cleans star, but it matches one or more occurrence of the pattern. The fifth one is grouping, using parentheses to group part of the regular expression together. This helps to the order of operators. This is the second part of question second. Complete the table with the correct regular expression. In this question, we have to complete this table by using the correct regular expression. So let's solve this question. So regular expression for regular language, L is equal to 0, 1 or 1, 1. The regular expression is 0, 1 plus 1, 1. For a regular language, L is equals to and 0, double 0, triple 0 and dash dash dash. The regular expression is 0 star. The regular language set of all string from A, B of length 3. The regular expression is 0 plus 1 plus 0 plus 1, 0 plus 1 plus 0 plus 1, 0 plus 1, 0 plus 1. For regular language, L is equals to 0 to n, or n is greater than equal to 0 is for this regular expression is double 0 asterisk. For regular language, L is equals to 0 to n plus 1, or n is greater than 0. The regular expression for this is a 0 of 0, double 0 asterisk. For a regular language, even palindrome, the regular expression is does not exist. This is the third part of question second. Explain Arden's theorems. The answer is Arden's theorem is fundamental result in formal languages theory and automata theory. It provides a method for solving system of equations that arises the context of regular expression and finite automata. Arden's theorem states that give two regular expression and over a finite alphabet, there exists a unique regular expression such that R is equals to Q or C dot R or cup P, where denote concatenation denote unique and that is regular expression without any occurrence of the string that is matched by R. In simpler term, if we have a regular expression representing a pattern and another regular expression Q representing a condition or constant, Arden's theorem allows us to find the regular expression that satisfies that the equation especially describe a recursive relationship between R and Q. Arden's theorem provides a systematic way to find the solution for R. The significance of Arden's theorem lies in its application in solving various problems in automata theory, such as finding the regular expression representing the language accepted by the finite automata or constructing finite automata. From regular expression, it provides a powerful tool for manipulating and understanding regular language and automata. This is the third question. In this question, we have to define the grammar for formal languages and we have to complete this table. So let's come toward the answer. So the answer is we have some type here, and for type 0, popular name of grammar is unrestricted and phrase structured grammar, and the condition and format of production rule is alpha beta, and alpha and beta are arbitrary length of string, and name of the languages is recursively enumerable language, and the name of recognizing automata is a Turing machine. And here we have a popular example also. And for the type 1, popular name of grammar is context sensitive and context dependent, and condition and format production rule is alpha beta, and length of b is greater than or equal to length of alpha, and mod of beta is greater than equal to mod of alpha, and the name of the language is context sensitive language, and name of the recognizing automata is linear bounded automata, and we have a popular example also. And for type 2, popular name of the grammar is context free, and condition and formal format of production rule is a to alpha, and name of the languages is context free language. Name of the recognizing automata is push down automata, and we have popular example also. And for type 3, name of the grammar is a regular language, and condition and format of production rule is a to w or wb. Name of the language is a regular language, and name of the recognizing automata is finite automata, and we have a popular example also. This is the question 4, which is define context free language and complete the table with appropriate grammar or production rules. So in this question we have some languages, and we have to find the production rules, or we can say grammar also. So let's come toward the solution for this question. So the answer is, uh, here we have languages, and the production rule for language L of G is S0, S1 or S01. For L of G is equals to W W star WE, 01 asterisk W asterisk is the reverse of W, equal to W of every string is even palindrome. The production rule for this is S0 S0 and 1 S1 0011, and for language L of Z is equals to WX W asterisk WE 01 asterisk W asterisk is reverse of W. For equal to W, every string is odd palindrome with X is middle character of string, and S is S0 1 S1 hashtag, and for language L of Z is equals to WWE01 asterisk. W contain equal number of zeros and ones. For 0 equal to 0110 1100 0011 0110 dash dash dash, and for this production rule is 0s10 1s01, and this is the fifth question. So the question is, take suitable example to demonstrate the following. The first one is leftmost derivation. Second one is rightmost derivation, and third one is ambiguous grammar. The first one is leftmost derivation. In leftmost derivation, at each step you replace the leftmost non-terminal symbol in the essential form. Let's consider a simple grammar. Now let's drive the string AB from the start symbol S. Here we always choose the leftmost non-terminal to expand, and the second one is rightmost derivation. In rightmost derivation, each step you replace the rightmost non-terminal symbol in the essential form using the same grammar as above. Let's drive the same string AB. Here we always choose the rightmost non-terminal to expand. The third one is ambiguous grammar. An ambiguous grammar is a grammar that can generate more than one parse tree for some sentence. Let's consider the simple ambiguous grammar. Now this grammar can generate the ABB in two ways. Parse 1 is AB, apply rule as AB, and A double B, apply rule B comma A to A. Parse 2 is AC, apply rule S to AC, and ABB, apply rule C B and A to C. Both parts result in the same string ABB, but with different structures. This ambiguity makes it challenging to determine the exact structure of the input string based on solely on the grammar rules. This is the second part of question 5th with reference of Turing machine defined with a suitable example. The first one is NTM, non-deterministic Turing machine. A non-deterministic Turing machine is an abstract computational model to extend the computability of the classical deterministic Turing machine. Unlike the Turing machine, which has a single transition for each input symbol in each state, a non-deterministic Turing machine can have multiple possible transitions for a given symbol and in a given state. When presented with an input, an NTP can explore computation paths simultaneously. The second one is a DTM, deterministic Turing machine. A deterministic Turing machine is a classical abstract computational model defined by Alan Turing. It consists of finite set of state and infinite tape divided into cells read or write. Head that can move left to right along the tape and set the transition rule to detect how the machine transition from one state to another based on the current state and the symbol read from the tape. In DTM, for each combination of current state and tape symbol, there is exactly one transition defined, making its behavior predictable and deterministic. The C is LBA, linear bounded automata. A linear bounded automata is a restricted version of Turing machine because where the input tape serves as the only tape available and read and write head can't move beyond the boundaries of the length of input string. LBS are particularly used for studying problems that involve bounded resources such as parsing context-sensitive language, where the limited tape prevents the machine from using bounded memory deposit this limit, and LPS have equivalent computational power of two Turing machines, meaning that they can solve the same class of problems. The question number 6 is, in this question we have to give two examples of each of the following. So let's come toward the first one is A, which is decision problem. In for this halting problem, give the description of a Turing machine M and an input W. Does M halt when give input W? Graph connectivity, given an undirected graph G and two vertices S and T. Is there a path from S to T in G? The second one is optimization problem. For this traveling salesman problem, given a list of cities and distances between them. What is the shortest possible route and visit each city exactly once and return to the original city. The second one is knapsack problem. Given a set of items, each with the weight and the value, determine the item to include the knapsack with fixed capacity to maximize the total value. The third one is undecidability. For this halting problem. As mentioned earlier, the problem to determine whether the Turing machine halt or the given input is undecidable. For this one more post correspondence problem, which is PCP. Give a finite set of diamonds, each marked with two strings. If there is a sequence of diamonds that can arrange to match the top string with the bottom string. The fourth one is P and NP. For NP polynomial time, problem like checking if a number is prime or shortening in the list of numbers can be solved in polynomial time. The graph pooling. In an undirected graph G and integer k can vertex of G be colored with the utmost k color such that no adjacent vertices share the same color. This problem is in NP but not known to be P. The fifth one, which is NP and NPC. For this subset sum problem, give a set of integers and a target sum. If there is a subset of integers and end up to the target sum, this problem is in NP. For this one more is a Boolean satisfiability problem. SAT. Give a Boolean formula if there is an assignment of to the value of the variable that makes the formula to true. This problem is NP complete, meaning that it is one of the hardest problem in NP. The next one is recursive language. A recursive language described by regular expressions such as the language of all string containing an even number of zeros. For this, one more is context-free language. Languages generated by context-free grammar such as the language of balanced parentheses. Now this is the question 7. In this question, we have to explain the following, which is the first one is Chomsky hierarchy, the second one is PDA, 2PDA and NPDA. The third one is recursively enumerable language. So let's come toward the Chomsky hierarchy. The Chomsky hierarchy is a classification of formal languages, which are a system for generating string of symbols according to certain rules. These grammars were proposed by Noam Chomsky, a linguistic and computing scientist. The hierarchy consists of four levels. The first one is type 0. Unrestricted grammar. These are the most powerful grammar where there are no restrictions on the production rules. They can generate any recursively enumerable language. The second level is type 1, context sensitive grammar. In this grammar, the production rules are such that they allow for the manipulation of a symbol based on the context of the string. This grammar generates the context sensitive grammar. The third level is type 2, context free grammar. Context free grammar have production rules where the left hand side consists of a single non-terminal symbol and the right hand side can be replaced by any string of symbol regardless of the context. CGFs generate context-free languages. And the next level is type 3, regular grammar. These are the simplest grammar where the production rules are limited to one non-terminal symbol on the left hand side and the string of the terminals and or single non-terminal symbol on the right hand side. Regular grammar generate regular languages. And the next one is the second part is PDA, 2PDA and NPDA. The PDA, which is push down automata, is a theoretical computer science concept which is used in the theory of computation. It is the extension of finite automata which is added state memory. FDAs are defined by the set of state, a finite set of input symbols, a finite set of state symbols, a transition function and start state and set of accept state. They accept languages generated by the context free grammar. 2PDA, two-way push-down automata. A 2PDA is a variation of PDA where the stack can be accessed from both ends. This means that the stack can be popped or pushed from either top or the bottom. NPDA, N push-down automata. An NPDA is a generalization of a PDA where there are n stack instead of just one. Each stack operates independently but can interact with the other through the transition function. This allows for even more computational power. The third part is recursively enumerable language. The recursively enumerable language, also known as recursively enumerable or computability enumerable language, are set of strings that can be recognized by Turing machine as language. L is recursively enumerable if there exists at least Turing machine that halt or accept a string belonging to L, or either halt or rejected or loops identity or string not L. Thank you everyone for watching the video.